How many times have you heard this phrase, my test passed? Your CI looks green, everything passes, you have great coverage numbers, and we feel a sense of accomplishment, a sense of confidence in our code, in our tests. And we ship with confidence. But what if this confidence is misplaced? What if test pass doesn't actually mean that the code is correct? Because this is the reality that we sometimes face. Our tests pass, but they let those guys slip into our code, those mutants, which are kind of like small bugs, and our tests are not capable of detecting those. We at Bosch, we develop safety-critical software for automotive applications, and we take those hard to spot and hard to get bugs very seriously. Today, I'll show you a way of how to detect those mutants, those weaknesses in your tests, to make your code more, or your tests more robust and more capable of detecting those hard-to-spot bugs, or those bugs creeping into your code. I'm Nico Eichhorn. I'm from Stuttgart, where Bosch is located. I'm a husband, father of 3, and I started my journey into software development during my studies of applied mathematics. And then in my 12 years now career in C++ software development, starting at the High Performance Computing Center in Stuttgart. And for another company, which is still doing automated test equipment for semiconductors. And in 2018, I started at Bosch in the automotive department. And we're developing advanced driving assistance systems. And properly testing your code is very essential in those fields, because in the end it's safety critical, so it may result in a loss of life, or if not that worse, loss of equipment or loss of money. So we need very robust tests which are capable of detecting the tiniest bugs. And that's where mutation testing can help us to answer the question, how good are our tests actually? So a bit about what we do at Bosch. We develop, as I said, advanced driving assistance systems, a stack for assisted parking and driving. And my team basically is doing similar to what Anthony was talking about on Monday. Sorry, not on Monday, on Thursday. We develop a central library, basically like a standard template library, which needs to be super safe so that everyone in the different teams can use it. And for that code, essentially, it's so important that it's safe, that it's robust, and that we have reliable tests for them as well. And we are excited for C++26 because it can make your code safer. However, it's still a long way to get there, unfortunately. So for now, the safety, or one of the ways to make our code safer is having really, really good tests and have effective tests. So what is this mutation testing then actually? There are some key definitions, or key concepts you should know about. So mutation testing is a technique to test the quality of your test suite by introducing small changes in your code, your testing, to introduce basically little bugs, which then should be detected by your test suite. And it's doing this by creating so-called mutants, which are variants of your original program with small changes. And those changes are defined by so-called mutation operators, which are basically rules for generating those mutants, like inverting comparison operators or changing logical operators or replacing function calls or changing constants and so on. So tiny changes, which I guess we all found in our code to be the source of a bug. And then in the end, also a big part is the test suite evaluation. We'll see, for those mutants, I was able to catch it. And then you can say the more I catch, the better is my test suite. And the overall goal should be to catch almost all of them, if that's possible, or at least as much as possible. So we already heard about fuzz testing a few times before. So what is the difference to fuzz testing then? Mutation testing focuses more on your tests. Fuzz testing focuses on your actual code, right? It introduces malformed or unusual input, whereas mutation testing changes your actual code. Both need some tools to set it up. It does not work out of the box probably with your testing frameworks. And the outcome is then, for mutation testing, you get an overview of where your test suite might need improvements. And fuzz testing will tell you, oh yeah, for this strange input value or for this, file which is malformed, you have a bug. So they are kind of related, but they have a different focus in what they are testing. And they are both a great addition to plain unit testing, but this one will be about mutation testing then. So mutation testing consists of basically 3 steps. We are generating those mutants by analyzing the original code and introducing those changes into it. Then those individual variants of your program are ran against your test suite. And then in the end, you analyze your tests by seeing how many have been killed and how many of those mutants survived. So before we get to the examples, there are some downsides and some upsides, or some benefits for mutation testing. Benefits being that it can help you to improve the quality of your test suite, to find those weaknesses in there and get rid of them. It can give you it can improve your confidence in your tests, so that you say, oh yeah, now it's green, that's great, because I'm really sure my test suite is good, so this confidence is not misplaced. And it also maybe gives you a different perspective on how to write your code, so your test code. However, some downsides is it's a bit of a performance overhead, because you need to run all the different variants of your code against your test suite, which takes, of course, more time than just running your unit tests. It can be hard to really analyze what is happening, especially if you have a really complex code you're testing, to maybe understand why this tiny little change made my tests pass, and maybe why did it not get caught by my tests. And it needs additional tools, as I said, to your testing framework to really automate it and maybe create a proper report on what you, the insights you just found. Right. So speaking about those tools, there are several tools for C++ which do the job. It's DexTool Mutate, Mu, CPP, Mul, Universal Mutator. And this concept of mutation testing can be applied to other languages as well. So you have some tools for different languages other than C++. And I've chosen this tool Mul because I found the setup was very easy. And it is, at least from what I experienced, it's the easiest to set up and to get your results very quickly. So how does it work then? So to give you a rough overview, it works with the Clang compiler. It basically will provide a plugin for the parse manager in Clang, which will parse and analyze your AST. And it will then integrate those mutants into the bitcode of your binary, and it will put in all the different mutants, those variations of your program, into the binary, into one binary. And it will make sure that it's all still correct syntax-wise and being executable. And then it will execute it in parallel against your test suite. And it will make sure that it's all isolated so you don't have any side effects by running your unit tests. So now to the example of how to use it and the kind of insights we found when we used it on one of our algorithms. So I have an example of which is inspired actually by something we did at Bosch. And we will be testing, or kind of testing the tests to a emulation algorithm of 32-bit floating point addition as of the IEEE 754 standard. So just a recap, how does this 32-bit float pointing number look like? You have 1 bit for your sign, you have 8 bits for your exponent, and you have 23 bits for your mantissa. So you have some special cases like not a number and infinity, where you have special, where you have all your bit set in the exponent. And you also have subnormal numbers, so very, very small numbers, which do not have an exponent at all, or no bit set for the exponent. And all those cases, they should be working in our algorithm. So when you get this input, it should give you the correct output. As a simplification, all results which are subnormal numbers, so being the exponent or 0, will just return a 0, just for simplification. And then if you want to play around with floating point numbers, or maybe kind of take a look again at how they are working, there's a great tool online, this float toy, which gives you this great visual overview of how it's composed, how those numbers are composed. So the algorithm basically can be summarized in 5 steps. So you have this special case filtering, like not a number and infinity, because it doesn't make sense to do your calculations when you have such a special number. Then if you're not having such a number, you need to align your exponents to basically then in the next step doing your mantissa addition or subtraction, possibly with some kind of cancellation or an overflow or underflow happening, which needs to be normalized in the next step. And then in the last step, everything is then put together in your output variable. And the input and the outputs are 32-bit unsigned integers, because those types are safe to do bitwise operations. So now, how will you then set up your project or your tests, your existing tests with this tool? First, of course, you need to get your program or your tool from their GitHub project. You need to create a config which says, oh yeah, I want to use those mutators to modify my code. And depending on what you're testing, you need to find out what are mutators or mutation operators which make sense. And you also want to exclude certain parts of your code, right? So you don't want to modify your testing framework, you don't want to modify your tests, because changing your tests when you want to test your test doesn't make a lot of sense. Right, and then you need to tell the compiler to use the tooling from MAL. So you need to define those 2 command line options, which is then telling the path manager of Clang to use this plugin, which will then basically infect your code by using the mutators defined in the config. And you need to tell MAL, or make it possible to MAL to extract the command line options used for the compilation, because it needs to make sure that the code is still valid after it applied the changes. Yeah, so that's how you set it up, and you can integrate it into your unit tests, and actually you don't need much more than just doing this. So some words about those available mutators. There are different groups you can use. There are so many individual ones you can use, like arithmetic operators, comparison operators, assignments, increment, decrement, function calls, which are replaced. And some additional ones, which I have not mentioned here, is like bitwise operators or boundary conditions like less than and equals will be changed to just less than, so you get rid of the equals case. And of course, logical operators, which get altered. So now, if you run your tool, you just run it against your binary, which you compiled. It will be doing some steps before the actual execution of your altered version. So it will be doing a warm-up run to maybe initialize some static caches or whatever. It will still do a filtering of what's actually going to be tested from those different variants of your code, or of your variants of your code to be tested. It will do a baseline run to see if your tests actually are passing, right? Because it does not make sense to have a failing test to detect any changes in your code. And then it will test all your different mutants, or all your different mutants against your test suite. And in the end, it will give you an overview of how many survived, how long it took, and a percentage number. So, and in my example, we had those mutants surviving, so like changing an equals condition or not equals condition to equals condition, changing a greater than to greater than equals. So every one of those lines might be a weakness in your test suite and a opportunity for improvement. And down here you see we have almost perfect coverage. So as you see, coverage is not everything. And you can have 100% coverage theoretically and do not test anything at all, because it just takes a look at, did you step into this function? If you did, yeah, great, but what about the result? That's not part of the coverage. So, but then, what do those mutants actually mean? So let's have a look. Yeah. So, I hope you can read it, but you're not that far away. Here we replace the not equals with equals. So this part of the code is where we check the, I can't read it on this screen, where we check the exponents and where we actually change the comparison for your mantissa. And this is the part of the code which is handling subnormal inputs, right? If you remember, the ones with the exponent being 0. And in this case, the equals, the changing to equals for the mantissa will also consider 0 as a subnormal number. So all the code or the algorithm parts which are only for subnormal numbers are now also executed for zeros. However, the faults introduced by that will then later be corrected when the mantissas are aligned for addition. So any test of a number just with 0 should fail, but however, in the code, it's then corrected as of the nature of the algorithm. So we do not see the result actually of those changes. So what do we need to add? We need to add a addition of 0 plus 0, because then the accidental change done by this mutant will not be corrected, and you will get an incorrect result for this test case we are seeing down there. So that was the first example of those mutants we just saw. So now here's a different one, or actually two different ones. Here we changed a greater than to greater than equals. And if you look at this code block, if the exponent is the same, this original statement will not be executed. But now if we introduce the equals condition here or here, we move into the first branch and we have a bit shift by 0 bits. Does not change anything. And also, if both of them are the same, it does not have an effect after. So with this change introduced, the first block and the second block being executed is the same as both of them not being executed. So this is a case where we cannot get rid of the mutant by, or maybe we can get rid of one of them, but we cannot get rid of both of them by refactoring the code, because this is an elemental part of our algorithm. So this is a case where we cannot improve our test suite to get rid of this. So that's maybe one thing to keep in mind. Not always your test suite is the weakness, but maybe it's just the nature of your algorithm. So for the next one, here we have the code part where, let me have a look. After the mantissa addition, where we possibly handle an overflow for the resulting mantissa. So we did have, so when can a mantissa overflow, right? If it's a very large number represented by the mantissa. And after the addition, it might be more than 23 bits. And that needs to be corrected, which is done after or in this while loop, actually. And to get there, to get rid of this one, we need to have a test with a very specific bit pattern. So maybe we thought about, for adding numbers, we need to make sure that we can have large numbers, which give us the correct result, but maybe we did not think about having this specific bit pattern here. So if we introduce this change in our code and we would run this test here, then you see the result actually of the addition of those two mantissas of those numbers would be the equals case of this comparison up there. So we would not go into this while loop for those two results, and it would not get normalized, and for those two input values we would get the same result as a result of the addition, which is plain wrong because the result should be this number, which is infinite. So we need to add this specific test case to get rid of this mutant here, or this mutated part of the code. So now for that's the last example I wanted to show. This is a place where that's after or just before we do the returning of the result, where we also handle the mantissa overflow. And here we changed the less than to less than equals, and the resulting exponent, or the exponent overall, can be 8-bit. So 255 is the max number. However, those exponent numbers are reserved for infinity and not a number. So they are handled beforehand, if you remember the algorithm. So we should not get to this case where it's just equal to 255 in this place. So this cannot be solved by adding new tests, but rather a refactoring, maybe. So we would need to change it to this one to introduce, so maybe just check for check just one number smaller. But in the end, is this better code than what we originally had, just for the sake of getting rid of those mutants, that's debatable. So now I'm really fast, but that means we have more time for the actual demo. So now, now I need to set it up somehow. Just a second. So okay, so where's my screen? Ah, yeah, there it is. So, hope that's also readable. Oh yeah, that's now. That's a bit tricky now. Okay, so here's the project I set up. In here we have our algorithm, which is doing the emulated floating point addition. So here we have our 5 parts, right? So here we extract all the information from our input values. We do the handling of those not the numbers and infinity special cases. We do the alignment of our exponents. We do then the actual mantissa addition or subtraction. We will then do the normalization, and then in the end we will all compose it into the end result. So now for the setup of the mutation testing, so it's a CMake project. Here you see your compiler commands you need to pass to it. I also additionally added some profiling options to it to get the line coverage, and just to really convince you that we have a great coverage. I can just show you all the code parts we are covering. So you see we have basically, at least from the line coverage, 100%. I think MCDC is not at 100%. Yeah, because we do not check those cases. But still, coverage is almost perfect. That's, at least if I think about automotive software, that's more than what we need, I think, when it comes to those ASIL levels. At least for ASIL B, that should be sufficient. And so now to our test suite, or test file. Down here, right, we have lots of cases. So I will be doing the conversion from unsigned 32-bit integer to those float numbers by just doing a bitcast. Right, we have several test cases, positive numbers, negative, positive and negative. 0 in the number. We have large numbers, really huge numbers, which go to infinity. However, those were not sufficient, as we saw. We have those subnormal numbers, we have small numbers, numbers with a flipped sign. We have infinity cases, we have not a number cases. So at least from, and then some additional ones to get rid of the mutants. But those are cases which one would, I think, consider on writing for such an algorithm. And is there something else to show? Yeah, I mean, the setup is quite simple. So now if we go to our build folder, right, we can I get it back? Yeah. If I make it and run it, right, we get the output. You see it's taking a reasonable time to execute. You get your results. Oh, actually, I think I skipped a... Did I skip it? Ah, yeah, I skipped it. But here we see a different mutant, but I can show it to you here. Maybe just increase it a bit. So here a mutant survived with a inverted bit shift. Strange, bit shifts. And it's about the result sign. So we're shifting our result sign to its position by 31 bits, and we did not notice when it was shifted the other way around, which would then be out of bounds. And so 0 is no sign, or positive, and 1 is negative. So it seems like we do not test for a negative result in our tests. Strange. So then if you look at the tests, now I need to find the place. Yeah, that's here. So previously our test was, it was subtracting a positive and a negative number, so something one would consider. However, our result is positive. So, and also another weakness, which I introduced on purpose. Here we do a addition of negative numbers, but we just check if the result is the same if we just flip those numbers as the input parameters. So we are testing basically the result with another result in your tests, which is something which can be dangerous, as in such a case, because we did not test for the concrete value. So, it's not, I need to see again which one was it. Okay. Up here, if I enable it, we compile it and run it, then we should see that this one should be gone. Yeah, and it's not there anymore. We have the other ones, but we already saw the ways of how to handle them. So just to really show you that they are that they can be removed, I will just enable all of them, run it again. And they are gone. And now we only have those 3 cases, which are due to the nature of the algorithm. So we cannot get rid of them easily or at all. But still, we now have a mutation score of 94%, which is, I mean, overall we had 56 mutants being introduced, and only 3 of those survived. So I think that's a good result. So that's something I think we can live with. So now back to the presentation. There we are. So, wait, now I need to go here. So yeah, we had our demo time. Now for the conclusion. Mutation testing can help us to improve our test quality. We found some improvements in our 32-bit float addition test. And we had an almost perfect coverage. However, we were able to find some edge cases missing. And we also saw that there might be some tiny room for improvement in the algorithm itself. And as I just showed you in the demo, it's easy to set up. I mean, in the end, it's just 2 additional command line options to your compiler and the config, and that's all. However, the analysis of your results can be time-consuming, right? Because depending on what algorithm you have, you need to find out, oh yeah, why is this change now doing this in your algorithm and so on, especially if you have very complex algorithms to test. And I was also trying to get the help of the AI to find this out. However, whenever, or in some cases, it proposed test cases which were just, it was just try and error. So maybe they misinterpret your code or your test suites, or they just hallucinate, whatever. That's a well-known phenomena of those AIs. So it can help you in some cases, but it might not be the quickest way of finding your results. I mean, in the end, it still makes sense that you fully understand your code. And of course, AI can help you with that, but you shouldn't rely too much on it. So, yeah, it can be used for this individual testing, like if you have a algorithm which is or a test case which is kind of smelly, which you don't trust that much, you can use it for doing the individual testing of this test suite because the setup is so easy. You do not need to integrate it into your CI pipeline for all your tests. Maybe it doesn't make sense for all of your tests because you might also have tests which or code you're testing which do not have that much potential for those mutations to be created, especially if you don't rely too much on those operators which mutation testing is changing. For instance, as I said in the beginning, it's only modifying your bitcode. So you cannot test anything happening at compile time with this testing approach. Of course, const expression is possible because you can also run them at compile time. But const eval is not possible. Everything else happening at compile time is just not possible to test with this. And also, another way which is now considered a good practice of doing stuff is via monadic operations. They also have some kind of logic in them with those else and and/or and so on. But that's something which they do not really reflect in those operators in your code. So again, it's a case where it's hard to really use mutation testing. Right, it's more time consuming, right? The analysis and also the execution, because as you saw, those test cases, they were taking, what was it? I think 2 seconds or so, whereas the test suite is just so quick. If you wanted to use in your CI, you can do analysis of Git diffs, and there are great ways of this small tool for reporting the results. You can put it into a database. You can send it to GitHub via some annotations and so on. There are so many ways of how you can report from it. You just need to find the way of how you want to do it. So if you really want to improve your test suites, then this mutation testing, you should try it, see for yourself if it can help you or not. And that's the end. Thank you. So, do you have any questions?
This is a little bit follow-up question to the const eval thing.
Yeah.
A lot of times you can do certain things that have like type safety around certain operations, like the std chrono time point cannot be crossed together; they can only be subtracted from each other. Does the mutation testing take that into consideration so that you can't do that switch or how does it work?
So you mean if you have like a custom operator or a user-provided operator, which there's no equivalent like less than, and then there's no greater than. Okay. I would guess that's what is happening during the analysis of your actual code, right? Because it has access to your AST and all that. I did not try this. That's a very good question. But I would expect that it would then see that this mutant cannot be realized because the equivalent is missing. Yeah, but still I would need to try this out. So just don't take it for granted, what I just said. Yeah.
Using those mutants, I imagine, could easily lead to undefined behavior. Is that somehow, and then everything after that, or before that, you cannot trust anymore? Do you know if the framework somehow handles that, or is it just you get what you get? And I hope you also extend the test suite without this mutation testing.
Yeah, that's what is done. So you mean that the changes introduced by mutation testing, they will then introduce undefined behavior, or if you have undefined behavior in the test suite beforehand.
No, after the mutations.
Okay. Okay. Yeah, I would guess that is something that would go unnoticed, and you would see this in the result of your tests, if it's visible. I mean, undefined behavior could also mean that a failing test is now passing, so in the end you would not notice it. If you have the feeling that there is something happening, you can still, there are more command lines to this tool where you can see all the mutants being created and where they are created. And then if you're suspicious, you can just introduce those changes on your own and then see if, really dig deeper into it, what's happening there. As far as I know, there's no way of the tool itself being capable of noticing this. Yeah. I mean, it could be an effect of a change. So yeah, undefined behavior could mean it's failing where it should not fail, or where it's passing where it should fail. So yeah, I think it just needs some manual examination to find it. Yeah.
Thanks for the talk. Oh, it's working now. What's the biggest project, biggest binary you've been using this tool on? Because I have the impression that it doesn't scale that well. It seems to be very expensive. So what's the biggest one you've used?
That's why I said it's. That's why I said it's. I mean, you are using it on unit testing level, right? So I don't think it makes much sense using it on a bigger level. I don't know if it's even possible. But yeah, I mean, in the end, you should have small unit tests. So we've seen this, I mean, it was, how many lines was it then? 150 lines, maybe, this algorithm, and we found 56. I mean, it's a lot of operators in this algorithm, so you have a lot of mutants being created, but if it's a huge binary or huge test, a lot of code to be tested, then yeah, it really does not scale that well, I guess. So then maybe you need to break it down, or yeah, I mean, then, yeah, actually that's something which I did not show. Maybe you've seen it, maybe you spotted it, because the tool is also capable of getting the coverage information. So it will only introduce mutations in the code you're actually covering. So you could break it down by disabling some tests, and by that reducing the coverage, just look at the parts of the code where you want to, where you suspect maybe some fishy things happening. Yeah, but yeah, unfortunately it does not scale that well.
Thanks for the talk. How do you actually deal with these mutants that you can't kill? Like, is there some kind of baseline supported by the tool where you just have a file and then it says which changes are fine? Or what do you do?
I mean, it has an export to SQL databases, or can't remember the format now. But if you have such a database, I guess you can just mark them as ignore them, and then the post-processing basically of those results can handle that. I mean, you can also tell the tool if it's a very isolated case, or maybe it's a very specific mutant which is causing this issue, or sorry, mutant operator, then you just can say exclude it and don't introduce those kind of changes in the overall project to your test suite. But I don't think you can do this on a more fine-grained level. I mean, again, by reducing the coverage, or using then different configs, because you need a config at compile time and on runtime, so you could use a different and more strict config for the actual execution of the tests to avoid those cases. But as of my knowledge, there's no way of marking them as ignorable in the first place.
I guess this question is similar to the last one. I just wonder if there's a way to say that if you have a custom assert-like macro or function, to tell the mutation testing framework that please do not change these, because these are more like part of the testing rather than the implementation.
Yeah, I mean, again, you can exclude mutators and you can exclude folders or files from it. So if it's in a very specific file, you could exclude it that way, or by, yeah. There are several ways, but not for this specific use case, which are intended for just your case, or your case. Okay.
Sorry, just to be clear, you're mutating the algorithm, not the test code.
Yes. Yeah. Just the unit under test, basically.
Right.
How many mutants will it generate, and will it somehow also combine those mutants, or only look at them separately?
No, you will get them separately. So it's one mutant per. So one. Yeah, it will try to keep them as small as possible, right? Because if you have two mutants, they could interfere and maybe mask the result of the other one. So it does not make a lot of sense to have them combined. Maybe it would save time, but it could then, yeah, hide the effects of one another. Yeah. Okay then. Thank you again.